So we're not going to learn anything new today. We're just going to do some review of the photoelectric effect and the Compton effect today, which I know both of those were probably pretty challenging subjects, but it's a matter of understanding what formulas you need to use and when, and then applying them as they are appropriate. Anyway, here's the plan for today. We're going to get some review of the photoelectric effect and the Compton effect. It's going to be a you try, I go over type of lesson. So in other words, please have a paper and a pencil ready and pause the video when I tell you to and watch them, and then watch my solution steps after you've tried the question, right? So in other words, make sure you're working through these problems, doing your best at them, and seeing if you're able to get them correct. And if you weren't, please reach out to me when this is all over, and I'll help you through anything else you need help with. Anyway, let's get going. Oh, the other thing, I'll just let you know right now, I just remembered, all of these questions, I kind of, took a cheap route today. All of these questions I've taken right out of your note package, right? Let's be honest here. I don't think there's any way we're all going to clear through them all, especially with the homework assignment that's been given. So anyway, on page 30, there's a question about the photoelectric effect that says light of wavelength 410 nanometers strikes a photoelectric surface which releases electrons at a maximum speed of 6.49 times 10 to the 5 meters per second. What is the work function of this surface? Well, let's just take a second here, pause the video first, and then I'll go over it. Okay, so what I'm going to do first is I'm going to set up pretty much a data bank of everything that I've got. So first things first, I know my wavelength is 410 times 10 to the negative 9 meters. Okay, that might be useful. We know that the electrons being released have a speed of 6.49 times 10 to the 5 meters per second. And we are looking for the work function. Okay. Now, what's important here is when light strikes a photoelectric surface, those electrons are released and they have a certain amount of energy. Now, the energy can be predicted using the formula E equals HF, but because there's a work function involved, because there's an amount of work that needs to be done to even have the energy of those electrons come out of here, you also have to subtract that work function, okay? That isn't on your formula sheet, but you just have to understand how to generate it. So the energy of those electrons coming out is equal to H times the frequency of your light minus that work that has to go into having this happen in the first place. Now we know what the speed of those electrons are, and that can actually be used to find our energy. Energy, in regards to electrons in this case, is actually your kinetic energy, and that of course is 1/2 mv squared. So maybe we could start by finding that kinetic energy and then plugging it into the rest of this. We don't have a frequency, but we do have a wavelength, but we can come back to that in a second. I'll just do it over here. EK is therefore equal to 1/2 times the mass of an electron, which is 9.11 times 10 to the negative 31 kilograms, and then times velocity squared, so 6.49 times 10 to the 5 squared. Just give me a second here. This means EK is going to equal, so 1/2 times 9.11 times 10 to the negative 31 times 6.49 times 10 to the 5 squared. This is going to equal 1.9186, we'll say, times 10 to the negative 19 joules. So that, of course, can now be plugged into this whole formula right here. Just by the way, frequency is the velocity divided by your wavelength for light, and of course your velocity of light. Maybe even change that to c for being the speed of light. So we can now just lump this all in one big go, okay? 1.9186 times 10 to the negative 19 is equal to h. And generally speaking, usually we would use electron volts, but you know what? We'll use joules in this one because it really does not matter. H is 6.63 times 10 to the negative 34 times the frequency, which I've just determined is well, c over the wavelength, right? So in other words, we can say that's 3.00 times 10 to the 8 over your wavelength, which is 410 times 10 to the negative 9, and then minus the work function. Bottom line is, if we want this work function, we have to add it over and then subtract this whole chunk to the other side and throw it all through. It's just a matter of algebra here, of course. Again, we're adding this over, subtracting this huge chunk over, multiplying all this through, and then subtracting. Basically, right, I'll just save you all the trouble. It is, or rather your answer should be 2.93 times 10 to the negative 19 joules. Now, if you actually instead used electron volts, which again is totally fine because your work function could be in electron volts, we can actually find that as well. You could just divide this by 1.60 times 10 to the negative 19 to turn it into electron volts. And of course, the answer in electron volts, I actually have it right here, is about 1.83 electron volts. So if you did it that way, that's fine as well. It didn't tell us what the work function had to be in, whether it was joules or electron volts. It could be in either one. I guess electron volts, I'll be honest, it's probably the better one. Usually electron volts is how we express work functions, but I digress. There you go. All right, next question. I really like this question, so I threw it in here. I'll read it to you real quick. A burglar knows an alarm in a certain museum makes use of the photoelectric effect. Ultraviolet UV light shines on a photocell with a work function of 5.01 electron volts. Any break in the light will set the alarm off. So in other words, if you don't have that much, or if you don't have an electric current flowing through the photoelectric cell, the alarm is going to go off, right? So the burglar realizes that if he can shine his own UV light source at the photocell, he can ensure that there is no break in the light and the alarm will not be set off. He obtains a UV light source with a frequency of this. Will he be successful in his burglary attempt? Explain why. I'll let you pause right here, give this one a shot. Think again about how any break in your flow of electricity, given this work function, will cause that alarm to go off. All right, so we're going to go over this one now. First things first, we know what our work function is. It's nice just making a little bank here. The work function is 5.01 electron volts. We also know the frequency of the light. The frequency is 1.13 times 10 to the 15 hertz. In order for this burglar to be successful, this light needs to at least overcome this work function, okay? So think again, even in the last question we did, we said the energy is equal to HF minus your work function. Well, the very minimum amount will be so that we have an energy that's just zero. So 0 equals HF minus W, or in other words, W equals HF. Now this formula, W equals HF, usually was W equals HF with a 0 here. In other words, our threshold frequency. The threshold frequency is the minimum amount of frequency needed to start the photoelectric effect. That's really what we're looking for here. We're looking for whether or not this actually meets our expectations of the photoelectric effect. Bottom line is, we don't actually even have to directly use our frequency here. We just have to see if the threshold frequency is comparable to this frequency here. Let me show you what I mean. So the work function we know is 5.01. We can set this equal to H times a threshold frequency. Now the H we use in this case definitely should be the one with electron volts. That's 4.14 times 10 to the negative 15. And then that's times by F0. Divide that over, and you're going to find that F0, your threshold frequency, should be about 4.67. Whoops, I goofed up. I just did the wrong thing. Let me try it again. 1 second. 5.01 divided by, this is real professional right now, 4.14 times 10 to the negative 15. There we go. That's better. Oh, geez, there I was thinking, like, what on earth am I doing? Threshold frequency should be 1.21 times 10 to the 15 hertz. Okay, that's your threshold frequency, 1.21 times 10 to the 15 hertz. How does that compare to the frequency of this burglar's UV light source? Well, it's more, right? Since this is more than his UV light source that he had right here, that means he's not going to have a strong enough light source to overcome the museum's security system, right? So in other words, will he be successful? The answer to this one is no. And to explain why, you could say his UV light isn't strong enough. Now, just to be clear on what I mean by strong enough, remember we even looked at with that little experiment app thing that I put in that lesson the other day. It has nothing to do with the intensity of the light. It has everything to do with the frequency of the light. So in other words, if he had something that was deeper into the UV spectrum, so a higher frequency, or in other words, even something closer to an X-ray light source, then yes, he would be successful. But his UV light, of course, isn't strong enough of a UV light. It's not going to work. Okay, moving on. This one's on page 32. It's another photoelectric effect question. Radiation with a frequency of 7.52 times 10 to the 14 hertz is used to illuminate a photoelectric surface in a solar panel. If the work function is that, notice it's in joules this time, what is the reversed voltage required to reduce the current through the solar panel to 0? This one's an interesting one. Pause the video here, give it a shot. Okay, so the reason I said this one was interesting is it has to do with voltage. Now, the only voltage that we've dealt with in here has been our stopping voltage, V stop. This is actually what it's referring to here. Having your current reduced to 0 means that you no longer have any current flowing, of course. So that would be your stopping voltage, just by definition, right? Now, the only formula we had that had stopping voltage in it said that your EK max is equal to QV stop, right? So in other words, your stopping voltage could be used to find your energy, okay? Now, during a photoelectric effect, we usually would say that energy is equal to HF minus your work function. Now, what's going on here, however, is that our energy is being stopped because of this stopping voltage. So in other words, it's in an opposite polarity. So in other words, we have to overcome the energy of this just in an opposite direction to get this to stop. In better, clearer English, your photoelectric effect is producing electrons that have energy in a certain direction, right? In order to counteract that, we have to have a stopping voltage that makes the kinetic energy go in the other direction. Now, yes, energy is a scalar. Usually it doesn't have a direction, but if we overcome an energy one way with energy another way, it still is going to be able to cancel it out. What I'm getting at here is your energy in both of these equations are going to be the same. And since they're the same energy, we can say, as a longer formula, QV stop equals HF minus W. Now let's take just a quick inventory of what we've got here. We have our frequency, we have our work function, H is a constant, Q is also a constant, it's just the charge of an electron. We're looking, because it says what is, we're looking for the stopping voltage. In other words, we're good to go here. We've got everything we need. So let's throw all this information in. Q, of course, the charge of an electron is 1.60 times 10 to the negative 19. V stop is what we're looking for. H, because we're dealing with joules, we're going to use the H that is in joules, of course, so 6.63 times 10 to the negative 34. F is in the question itself, 7.52 times 10 to the 14, minus the work function, which is 3.52 times 10 to the negative 19. I would calculate the right-hand side of this equation first, and then get that answer and divide it by this 1.60 times 10 to the negative 19. Bottom line is, though, V to 3 sig digs is going to equal 0.916 volts. I guess that should be V stop. V stop is 0.916 volts. Good. All right, we got one more question we're going to do here. This one's on page 40. It's going to be the only Compton effect question we do here. An X-ray of wavelength 0.010 nanometers scatters at 60 degrees after colliding with a stationary electron. What is the wavelength of the scattered photon? Pause the video here, give it a try. All right, so since we're looking for a wavelength of a scattered photon, first of all, let's understand that this is our initial wavelength, okay? The X-ray of wavelength this, that was initially, it's gonna have a final wavelength that changes. Now, we have a formula on our formula sheet that says delta lambda, so a change in wavelength, is equal to H over MC. Sorry, my phone just started ringing here. Throw that away. H over MC times 1 minus cosine theta. Now let's just take inventory of what we've got here on this one. H, of course, is a constant. M is the mass of an electron, so that is also constant. C is also a constant. That's why I said the other day, it's like H over MC. Why don't we just like call this one big constant? I have no idea, right? It probably does exist. I just don't know what it is, and I'm kind of too lazy to calculate it right now. So let's figure this out. This will tell us what our change in our wavelength is here. Let's throw this all in because we have all this information. Is what I'm getting at here. So H we should use with joules just because that's usually how we would do it. It's just a standard unit, of course. So we'll say 6.63 times 10 to the negative 34 over the mass, which is 9.11 times 10 to the negative 31. C, which is 3.0 times 10 to the 8. All of this, and I'll put it in a big chunky bracket right here. We're going to multiply that by 1 minus cosine of your angle. Remember, theta is what your photon scatters at. So it is your 60 degrees. We're good. There's no trick there. Okay. Throw this in your calculator. You're going to find, after I do this here, once again, 6.63 times 10 to the negative 34 divided by 9.11 times 10 to the negative 31 times by 3.0 times 10 to the 8. This must be really exciting for you guys. Very exciting. Times by 1 minus cosine of 60. This gives me delta lambda equals 1.21295 times 10 to the negative 12. That's your change in your wavelength though. Okay, so your change in your wavelength is equal to this. Remember, your change in your wavelength means your final minus your initial. equals that 1.21295 times 10 to the negative 12. We have our initial wavelength though, so we just need to add that over to the other side. So we know our final wavelength is going to equal 1.21295 times 10 to the negative 12, plus our initial wavelength, which was this many nanometers, so 0.010 times 10 to the negative 9. Adding those together, 0.010 times 10 to the negative 9, gives us a final answer, finally, of lambda f, final wavelength, equals to 3 sigdigs, I believe. Nope, 2 sigdigs. 2 sigdigs, interesting, yeah, just 2 sigdigs. 1.1 times 10 to the negative 11 meters. That would be the final wavelength of that X-ray photon. Woo! If it even is still an X-ray. I think it still would be an X-ray at that, but we're good. All right, anyway, we're done for today. So for practice, I want you to continue working on the EMR assignment. Remember, that is due on Monday, May 11th. And I want you to complete any of the practice problems from the last 2 days. Again, we just took a few selection questions out of there. So that's kind of eased up your workload on that, but please make sure you're getting these questions done. That's where your practice is going to be, and the answers are in there. The answers are also posted on the Google Classroom page. Compton effect would be a good one to pull from. I only did one Compton effect question today because there really isn't a lot of Compton effect questions that are in there. So those could be quite easily completed in not a huge amount of time. Easily is not the good word, just less amount of time because there's not very many of them. Photoelectric effect, however, though, there's a million of those questions in there. Pick away at them, that's for sure. EMR assignment, though, is your priority. That's what I'm getting at. Anyway, as always, if you have any questions, please contact me, and best of luck.